It's the early 1930s. Soon, the Second World War will start. Large bombing runs by military aircraft are used more and more by military strategists. However, the problem with large bombing formations, though, is that they still rely solely on visual target identification, which isn't as difficult as you might assume. Targets such as cities and factories aren't small, and they can be spotted quite easily from the sights of most bombers. However, the capability of running air raids during the night is still very difficult. Still, the concept of night bombing strategic campaigns began to become paramount in military aviation circles. The main reason for this is the increasing capability to strike across Europe with useful bomb loads. As bomber squadrons are slow and lumbering, they fall prey to interceptors easily if spotted by the target nation's military. Therefore, the capability of running night raids would be of immense usefulness to any air force. A bomber painted in black would be near impossible to spot in the night. You need to get extremely close to notice it. Therefore, bombing runs could be performed with less chance of interception if ran in the night. The problem still persists though. Identifying targets in the darkness of the night is extremely difficult. The same goes for holding formation and determining one's position for that matter. To support this mission, the RAF, Royal Air Force, invested heavily in the training of pilots and weapon officers with the target of improving their nighttime performance. They started equipping the aircraft with more expensive navigation aids, including Astrodomes. The Astrodome was a fairly recent invention around the time of the Second World War. It entered use in the 1930s by the British. An Astrodome was basically a system to adapt a sextant for use in an airplane. So they outfitted planes with plexiglass bubbles on top that could enable a 360-degree view of the horizon. And navigation, celestial navigation, became most important during nighttime operations where there was no way of using landmarks for navigation. They had to use sextants with the stars to determine the actual position. But, of course, this was a bit more complicated than the traditional use of sextants in ships, because the viewer is not level with the horizon, but looking down, and of course it changes depending on the altitude. So they had to adapt a special kind of sextant for this use. These contained highly advanced machinery. This part contained a complex clockwork that actually managed to average various readings in a mechanical computing way. This enabled an error-free measuring because all the random errors were averaged out. And the right side here is the sextant proper, which contains the necessary mirrors and pointing equipment to measure the angular distance between the stars and the viewer's position, thus enabling accurate positioning. Another thing bombers became equipped with were illuminated workspaces for the navigation room. This was needed so the navigator could perform the calculations needed for determining the aircraft's exact position. All these improvements were installed in the bombers of the RAF as the war began. In reality, though, most bombs missed their target by many miles. It was a complete failure as little progress was made. So as night bombing became more and more of a necessity with the ever-increasing bomb load bombers could carry, a solution had to be found. Night bombing is extremely difficult as identifying the targets in pitch black is near impossible. That is, if you even manage to make it to the target due to the difficulty of nighttime navigation. And this is not even considering the complexity of holding flight formations with black planes in a black sky. The RAF's approach turned out to be a failure. However, the German Air Force, the Luftwaffe, did not take such a fatalistic view of air warfare. They invested heavily in research for accurate bombing technology. They required a solution that was capable of hitting small targets like depots and factories during nighttime operations. Unlike the RAF, the Luftwaffe realized the limits of celestial navigation in regards to precise targeting. As not to depend on it, they focused their research on radio-based navigation, a brand new technology at the time. Throughout the 1930s, they concentrated their research efforts on a bombing direction system based on the so-called Lorentz concept. With this new technology, it became relatively easy for planes to navigate in the dark. All they had to do was listen for radio signals, and the best thing about it was that the necessary radios were already being installed on many aircraft at the time, making it a very cost-efficient solution. The Lorentz beam navigation system was developed in the 1930s in Germany. It enabled blind landing, which means that a pilot does not need to rely on any sort of visual identification for correctly landing an aircraft. This is, of course, very useful during nighttime operations and even during bad weather conditions. The system consisted of 3 antennas set up at the end of the runway. The antennas each broadcasted a signal. The middle antenna represented the correct landing area. It used a continuous signal. This area I represented in green. The other 2 antennas also supplied their own signal, but these areas represented the incorrect areas of the edges of the runway. As I said before, the middle supplied a continuous broadcast, but the ones on the edges were far more interesting. They were connected by a mechanical rotary switch, which constantly disconnected and reconnected the electrical wirings. This resulted in one of the antennas broadcasting a dash signal and the other broadcasting a dot signal. Because the rotary switch rotated between these 2 antennas, these signals perfectly compensated each other and filled out the empty areas. The dashes lasted 7/8 of a second long and the dots 1/8 of a second. So when a pilot started flying in, if he stayed on course, he would hear a combination of the dashes and dots, resulting in an equal signal tone, which was also called the equisignal. But if he veered off course, he would start hearing only dots or dashes. This way he could quite easily find the middle of the runway just by using his ears alone. The reason the Lorentz beam principle was necessary with its overlapping beams was because the sharpness of the beam increases approximately logarithmically with the length of the aerial array with which it is generated. A law of diminishing returns operates such that to attain the sharpness achieved by the Lorentz system with a single beam, approximately 1 mile wide over a range of 200 miles, an array of prohibitive size would be required. Lorentz had a 30-mile range, approximately 48 kilometers. This was enough for blind landing, but nowhere near good enough to run actual bombing raids over the UK. Though this is easily fixable by increasing the transmit power of the system and installing more sensitive receivers. As the Lorentz system was designed for landing planes on runways, The beam was set wide enough so that it could be used even some way off the center line of the runway. Normally this is not a problem. As an aircraft approaches the runway to land, the distance decreases. As the distance decreases, the beam width becomes smaller, thus increasing accuracy. Therefore, the closer you are, the higher the accuracy. The problem is, for air raids, the opposite is required. The accuracy near the station is not important. However, the accuracy must be sufficient to hit one's target when the plane is far away, not close. As it stands, the accuracy was at a maximum over the target. A new system had to be developed. And so they did. The German Air Force, the Luftwaffe, modified the Lorentz system. The new solution was called Kneckerbine. The modifications that had to be done to create Kneckerbine were actually fairly minor. First, the German engineers installed many more elements, making the antenna much larger. With this modification, the required accuracy was provided. The important thing is, though, they retained the capability to alter the beam's direction ever so slightly by switching two reflector elements. In fact, the change to the beam angle was so dramatically reduced that over the target it was only a few tens of meters wide. This new antenna was also what gave Kneckerbine its name. The shape of the aerials resembled a crooked leg, which in German can be called Kneckerbine. Kneckerbine is also the name of a magical raven in German mythology. Now that the accuracy problem has been solved, they had to increase the transmitted power considerably. This was quickly done by German engineers, while still making them look like ordinary blind landing receiver systems. And this fact was very important. Should the existence of Kneckerbine become known to the Allied forces, it would be an easy target for their bombers. Therefore, disguising them as normal landing assistance systems was paramount. The Kneckerbine system had two transceivers. One of them would guide them towards their target. However, it could not tell them how far they are from the station or the target, only the distance from the center line. It was set up in 1939 on nearly the most western point in Germany. A second transceiver, many hundred miles away, was built only a year later, in 1940. The beams of the first and the second transceiver would cross over the raid target. The bombing formations would first follow one of the beams. As soon as they picked up the second one, they knew they were very close to the target. Once they were in the center line of both rays, they knew they were right above the target. The only thing they had to do was drop their bombs at the right time to account for their inertia, and the target was destroyed, thus making it relatively easy to perform nighttime operations. This capability to bomb targets in the darkness of the night was an immense tactical advantage. Black painted planes were near impossible to spot by interceptors in the dark. In effect, many targets were destroyed without even an air siren going off beforehand. Some time has passed. The Kneckerbine system has been used to a great extent with great results. However, due to the state of avionic technology at the time, it was still common for a bomber to crash during a raid. One such bomber was investigated by the British Air Ministry after it crashed in England. It was then that the British intelligence at the Air Ministry analysed the plane they found something unexpected. They realised that the Lorentz system installed was much more sensitive than required for mere landing assistance. They also had secretly recorded transcripts from German prisoners of war pilots. With the help of these transcripts, they concluded that the system must be used by Germans as a bomb-aiming aid. Their suspicion was confirmed when Winston Churchill, the Prime Minister, had been given ultra-intelligence from the decrypted Enigma machine. The messages mentioned bombing beams. When the head of the Air Ministry at the time, Jones, mentioned the possibility of bombing beams to Churchill, the Churchill quickly ordered further investigation. The yet unknown system had been given the fitting codename Headache. However, the idea of Kneckerbine, or headache, as the British intelligence called it, was not without controversy. Many in the Air Ministry believed such a system to be impossible with current technology. Frederick Lindemann, the leading scientific advisor to the government, argued that the system would be impossible. His argument was that the curvature of the Earth would prevent such a system from reliably guiding the bombers. Thomas Lidwell Eckersley of the Marconi Company, a British telecommunications engineering company, disagreed, however. In his opinion, such a system was a very valid possibility. The sole possibility of such a system posed a very real threat. The Air Ministry had to consider it, at least after receiving all the evidence pointing towards it. The Enigma message, transcripts from the German prisoners, the over-engineered Lorentz system on the downed German bomber, all these things pointed to the existence of the headache system. Thus, hard evidence was required to solve the mystery. Eventually, Churchill ordered reconnaissance flights to try and detect the beams. This, however, was not an easy task. To detect the 30 to 33 MHz Lorentz signal, the receivers were required that the RAF did not have at the time. And in addition to the missing receivers, there was also the difficulty of locating the beams, which were only tens of feet wide over the vast skies of England. Still, without the required receivers, it was not possible to detect the beams. Luckily, a small shop in Lyell Street in London had an American amateur radio receiver, the Hallicrafters S-27, and as it just so happens, this receiver was capable of listening to 30 to 33 MHz signals. The receiver was quickly fitted into an Avro Anson, a British twin-engine, multi-role aircraft by the British Y Service. Now that there was an aircraft ready to try and detect the signal, there was nothing in the way of the British Air Ministry finding the beams. All they had to do was go up, search, and see if they found it. If they did, it would be a valuable discovery. However, with the plane ready to go, the flight was almost cancelled. Eckersley, from the Marconi Company, withdrew his claim. He had previously disagreed with Lindemann's claims that such a system would be impossible, stating that Lindemann was wrong in believing the beams were impossible due to Earth curvature. Eckersley, from the Marconi Company, asserted that the beams would bend around Earth. However, now he retracted this assertion, and the future of the reconnaissance flight was in a slippery slope. Luckily for the British, R.V. Jones, head of the Air Ministry, saved the flight by pointing out that this flight was ordered by Churchill himself, and he would make sure that Churchill would get to know exactly who had cancelled it. Thus, the flight continued. The crew were told to simply search for any signal around 30 MHz having Lorentz characteristics. If they found it, they were to determine its bearing and return with the information. Now, there was nothing in the way of the British detecting the German beams. The reconnaissance plane was flying above England with its receivers armed and searching for the beams. And so they did. Eventually, the crew found a 31.5 MHz beam from Kleve, and subsequently found the intersecting beam from Stolberg. They had found both beams. The navigator and the radio operator of the flight determined the path of the beams and discovered that they intersected above the Rolls-Royce engine factory in Derby. At the time, the only factory producing the Merlin engine used in British planes. They also discovered the origin of the beams, and that the discussion of whether the beams would bend with the Earth was irrelevant, as the base stations were basically in line of sight to the target. After locating the Kneckerbine beams, named Headache, a new operation went under name codenamed Aspirin, was the British effort to block the Kneckerbine system. Of course, British efforts were concentrated on jamming or interfering with the German radio signals. After all, the Kneckerbine system was the cause for more precise bombing raids by the German Luftwaffe. It was quite obvious that the British would try to interfere with the system. The first step in the British defence project Aspirin were two Avro Anson planes outfitted with radio receivers. These planes would fly around, trying to detect the Kneckerbine beams over England. Once they found it, multiple transmitter stations like broadcasters were informed. Their job then was to send fake dot signals towards the Kneckerbine target. The low-powered signals sent by the British could then be heard by the German navigators on board the bombers. They would hear two dots with absolutely no easy way to distinguish between them, except by comparing them with a known location. Later on, the British went one step further and synced their dot transmissions with the German ones, thus making it absolutely impossible to tell which signal was which. This worked with great effect. The fake dot signals sent by the British could not be told from the real ones. Bombers would in turn drift, of course, leaving the bombing line and drifting into the dash area with no way to correct it. It was almost like the beams were seemingly bent away from the target. Eventually, the British became so good at creating the fake signals that they could incline the beams by a controlled amount, therefore leading the Germans into dropping their bombs where the British wanted. This made it possible for the British to let the Germans drop their bombs into uninhabited farmland, forests, or even lakes. One of the reasons the British fake signal was so effective is due to the fact that many German navigators were trained solely to follow the beams for navigation. The crews often failed to find a true equi-signal, or even Germany for that matter. In fact, there were even records of German bombers landing at RAF airfields in England. As good as the Kneckerbine system was, the Germans never intended it to have a long-range role. While Kneckerbine was in use, Johannes Hans Plendl, a German radar pioneer whose navigation inventions made the early German bombing success possible, was working on a much more accurate version to replace it. The new version was developed with the target of being much more accurate. The system in development was the so-called x-gerät, or X device. The basic idea behind the x-gerät was similar to Kneckerbine. In fact, it was developed on the same basic concept. But this time, there were more beams. The German x-gerät was composed of the main beam and a series of intersecting lines. The idea was simple. Bombers would follow the main beam. Once they heard the first intersecting beam, the navigator would prepare himself and set up his equipment. Once the signal by the second beam was received, a double timer started counting up. Upon the third signal, one of the timers would stop and the other would reverse, counting back down to 0. The now stop clock would give the travel time from the second to the third beam. Now, the bomb point was located at the same distance from the third beam as the second. Because the bombers flew at a constant speed, once the now reverse clock hit 0, the bombing crew knew they had to drop the load. They were now on the release point. This simple system allowed them to drop their bombs at the correct point to hit the target. And because it was difficult to call the lines by their number, they were given code names based on German rivers. The main beam was called Weser. The intersecting first, second and third beams were Rhine, Oder and Elbe. Additionally, the Excarate itself operated at a much higher frequency, around 60 MHz, thus requiring new radio devices, as there was not enough equipment available to outfit all the planes. The experimental unit Kampfgruppe 100, literally Fight Unit 100, was formed. To do this, the Kampfgruppe would first attack alone to drop flares on the target. The bombers would then follow and bomb the bright flares optically. Eventually, on December 20th, 1939, the system was put to the test. Would the German engineering be successful? The first bomber to try the system was flown by Oberleutnant Hermann Schmidt from the Kampfgruppe 100. His task was simple, in theory. Use the x-gerät to fly over London at 23,000 feet altitude. And so he did. In the end, he concluded that it was a total success. Following the first test, many effective raids were conducted. The initial series of bombings were called the Moonlight Sonata by the Germans. Among its targets were Coventry, Wolverhampton and Birmingham. All of them were a total success. In fact, the system was so successful that post-raid analysis by the British intelligence showed that one of the raids conducted by the Kampfgruppe 100 alone dropped their bombs within 91 meters of the midline, spread along for a few hundred yards. Such accuracy was difficult to achieve even during daytime bombing. The attack on Coventry, with flares and full support from other units, almost destroyed the entire city centre. With these new weapons, the Germans had the capability to do precise strikes during nighttime. Almost impossible to be spotted by the British, it was incredibly useful and a very powerful tool in the war. However, the success of the Excarate would not last long. One fateful day in 1940, a German plane crashed over England. A plane that was equipped with the Excarate on board. Although the aircraft sank, the Excarate equipment was recovered. This device was fitted with a very sharp filter, which was sensitive only at 2000 Hz, and not to the early British 1500 Hz counter signals. The British intelligence understood implications and fast discovered the workings of the Excarate, and so the British engineers got to work, trying once again to stop the German air raids. Eventually the Excarate was defeated by way of a false Elbe, which was set up to cross the Weser guide beam at a mere 1 kilometer after the Oder beam, much earlier than the expected 5 kilometers. Since the final stages of the release were automatic, the clock would reverse prematurely and drop the bombs kilometers short of the target, and so the British engineers had once again bested the German system. However, the Germans were not done yet. British monitors soon started receiving intelligence from Enigma referring to a new device known as EpsilonGreat, which was also sometimes referred to as Wotan. The analyst realized Wotan referred to Vidden, a one-eyed Germanic god, and might therefore be a single-beam navigation system. The EpsilonGreat used a small narrow beam pointed over the target, similar to earlier beam systems, transmitting a modulated radio signal. The system used a transponder that received a signal from the beam and immediately retransmitted it back to the ground station. The ground station listened for the return signal and compared the phase of its modulation to the transmitted signal. This is an accurate way of measuring the transit time of the signal and hence the distance to the aircraft. Coupled with the direction of the beam, the bomber's position could be established with reasonable accuracy. The bombers did not have to track the beam. Instead, the ground controllers could calculate it and give radio instructions to the pilot to correct the flight path. Side fact: Jones later learned that his guess on the operating principle based on the name Wotan was entirely by luck. Later documents showed that the original X-gerät was known as Wotan 1 and the EpsilonGreat as Wotan 2. Had he known the name he was also associated with, the X-gerät, it was unlikely he would have concluded the system used a single beam. Nonetheless, the British were now ready for the system even before it was used. Additionally, as luck would have it, the Germans had chosen the operating frequency of the Wotan system very unfortunately. It operated on 45 MHz, which just so happened to be the frequency of the powerful but dormant BBC television transmitter at Alexandra Place. All Jones had to do was interrupt the signals, was arrange for the return signal to be received from the aircraft and then sent to Alexandra Palace for retransmission. The combination of the two signals modified the phase shift, and thus the apparent transit delay. As EpsilonGreat's use went on, the aircrew accused the ground station of sending bad signals, and the ground station alleged that the aircraft had loose connections. The gradually increasing power conditioned the Germans such that they didn't realize that anyone was interfering with the system, but believed that it had suffered from several inherent defects. The Luftwaffe, finally realizing that the British had been deploying countermeasures from the very first day that the system had been activated operationally, completely lost faith in electronic navigation aids, just as the British had predicted, and did not deploy any further system against Great Britain. And as we now know, the war would soon come to an end. Thus, our story about the German air raids on Britain comes to an end. It was really interesting to see Germany and England play a game of catch on this technology, and we hope you enjoyed this video as well. Have a good one.